So, our first topic today for combinatorics will be casework, which is often a crucial part of all sorts of computational counting problems. So, just a brief sketch of the principles of casework. It's often not the nicest way to solve problems. There are possibly cleaner ways to do it, but sometimes there are not many other obvious ways to approach a problem. So casework is a reliable tool to fall back upon whenever you feel the need to. However, since casework can get messy, it's important to keep everything simplified. On the AMI, lots of combinatorics problems is just test how well you can keep your cases simplified and disjoint so that you don't miss a case or you don't overcount a case. So if you can simplify cases, for example, by merging them together or splitting them apart to make them more clear, do it in order to ensure that you're accurate and quick about it. Before you jump into excessive casework, just sanity check your approach to make sure that it's both feasible, not too error prone, and won't take too much time. And when you're carrying out your casework, be very careful. A good idea is to use a separate sheet of scratch paper and clearly mark off, for example, drawing off sections, each case so that you don't mix any cases, and make sure that you set up all your cases at the beginning before computing so that you don't miss or overcount any case. So the basic gist is be careful and do it systematically. So let's get started on our first casework example. So here is a problem, and I'll give you a little time to read it. If you want, you can, once you finish reading the problem, you can start thinking about what cases to set up. And if you do that, try carrying out a couple of the cases. We're having a couple of technical issues right now, and we'll be back shortly. Okay, so we're ready to continue. Sorry for the delay. So we want to fill in a grid with non-negative integers such that no non-zero integer appears more than once in any row or column. So how might we want to begin? Well, as you might have seen, we're going to, because we want to take cases, we need to first figure out what ways we can fill a row with. So it turns out that there are only these 5 ways to fill out a single row or column, up to permutation. And also note that the last one is the only one that doesn't contain any zeros. So let's try to take cases. Well, it's in this situation, it's more reasonable to try to consider what happens if we have a large number first, because the large number limits what we can have in the grid. So suppose that we have a 7 in the grid. So there's a 7 0 0 row and a 7 0 0 column. So what does this grid look like? Well, in this case, the row with the 7 has to have a 7 and 2 zeros, and the column with the 7 has to have a 7 and 2 zeros. So in particular, if you draw it out, I would recommend doing that right now. So if you put a 7 in the grid, then the other 2 spaces in the same row have to be 0, and the other 2 spaces in the same column have to be 0. So this leaves only 4 empty spaces that we need to fill. And these 4 spaces are the vertices of a 2 by 2 square or rectangle. So how many ways can we fill up this 2 by 2? What does the structure look like? Well, in particular, there's a couple of options. Either this is the only 7 we have in the grid. If it's the only 7 we have in the grid, then we have 1 7. Suppose there's another 7 in the grid. Try filling in one of the 4 empty squares with a 7. Well, that just tells you that you have to have more zeros. And in fact, there's only 1 empty square left. And that empty square has to get filled with a 7, because the other 2 squares in the same row are 0. So if we have another 7, then we've got to have 3 7s, and all the rest is 0. So if we have 3 7s in the grid, how many ways can we fill in the grid? Well, we can have, it's simply just a permutation of the rows. We have 3 places to put the 7 in the first row, then 2 places left to put in the second row, and 1 place for the final row. If there's only a single 7 in the grid, well, let's pick one of the one of those 4 empty squares. Well, we can put any number we want in them. So there are 6 ways to do that. But once you put a number in it, then that fixes the rest of the grid. You can use the rules that were given, and you'll find that there's only 1 way remaining to fill out the grid. So basically, there's 7 ways to put the, there's 9 ways to place the 7. And then we can choose any of 1, 2, 3, 4, 5, 6 to fill in the one of the 4 squares. And that fixes the entire grid. So in total, there's 9 times 6 ways for that. Now, for this case, we have a total of 60 grids. So there are 60 working grids that have a 7. Any questions so far? Well, if not, then we can move on to the next case. So we've gotten rid of the case where there's a 7 in the grid. So now we're assuming that there is no 7 in the grid. Well, the next natural step is to consider what happens if we have a 6 in the grid. So what does the grid look like? Well, we have to fill it in with the row with ones and zeros and the column with ones and zeros. So the grid looks something like this so far. So if we use the same reasoning, suppose that there's another 6 in the grid. You can check that if you put the 6 anywhere, then the rest of the grid is fixed and there's actually going to be 3 6s in the grid. So there's either 1 6 in the grid or 3 6s in the grid. So if we have 3 6s in the grid, how many ways are there to fill in the grid? Well, we have to put the 6s such that no 2 are in the same column or the same row. There ends up being 6 ways to do that. Now there has to be a 1 in the top row. And then you'll find that no matter where you put the 1, the rest of the grid is fixed. So once we pick the 6 possible ways to organize the 6, and then the 2 possible locations for the 1 in the top row, then the grid is fixed. So it ends up being 12 ways if we have 3 6s. What happens if we have 1 6? Well, if we look at the grid up top, then how many ways are there to fill in the 4 question marks with non-6s? Well, if we take a look at the 1s, if 1 is in a row, then then the other ones in this row are either 0 6 or 1 4. But we assume there's only 1 6. That means you have to fill it in with a 2 and a 4. And you can see that in the example we have, if we choose which order we put the 2 and 4 for the second row, then that's going to fix the rest of the grid. So for the given grid we have 2 ways to fill in the question marks if we don't use the 6. But there are different places we can choose to put the 6. There's 9 places we can put the 6, then 2 ways to locate the 1 in the same column, then 2 ways to locate the 1 in the same row, and then finally 2 more ways to flip the 2 and 4. So it ends up being 9 times 8. So if we add up the cases, we end up with 84 ways for a 6 if we have a 6 in the grid. So now we can assume that there's no 7 in the grid and no 6 in the grid. Naturally, we'd move down to 5. So what happens if we have a 5 in the grid? Well, then you have to have a 2 and 0 in the same row and column. So the grid looks like this. This ends up being basically the same as our previous case. So we have to have either 3 5s or 1 5 using similar reasoning. If this is the only 5, then that's good. If there's another 5, then you can check there have to be 3 5s. Now, if there are 3 5s, then it ends up being the exact same situation as our previous case with 3 6s. There's 12 ways. But if there's only 1 5, then it's a bit different. This time, we're not allowed to use 6s or 5s. So the only possible ways to fill the other rows are 0, 3, 4, and 1, 2, 4. Now look at the second row. The two question marks in the second row have to be a 1 and 4 in some order. But the leftmost question mark can't be a 2. It can't be a 1, because then the bottom question mark would be a 6. So that means the second row has to be 4, 2, it has to be 4, 1 in that order. And then you can check that that fixes the grid. So in the grid we have shown, there's only one way to fill in the question marks. And that means that once we plop down the 5 and assign the 2s and 0s, there's only one possible grid. There's 9 places we can put the 5, then 2 ways to put the first 2, and then 2 ways to put the second 2. So that ends up being 9 times 4. So when we add them up, we get 48. And then if there's no 5, then the only ways we're allowed to fill a row are 0, 3, 4, or in 1, 2, 4. If we have a 0, 3, 4, then it ends up being basically the same as the first half of the previous cases. There's 12 ways. And 1, 2, 4 ends up being the same. You want to you permute the 4s, and then you can pick 2, and that's it. So we'll be glossing over slightly, but these cases are not as difficult compared to the previous ones. So just notice how we took casework basically on the largest number in the grid. So we went from 7 down to 6 down to 5, and this way we could keep our work organized. We wouldn't get confused or miss cases or overcount cases, because we're always considering the largest number in the grid. If we add them all up, we get a total of 260. Are there any questions? Yes, there is a better way to solve the problem that we'll be talking through right now for instructive reasons. But this is probably a more reasonable one to come up with in contest. So an easier approach is there's 5 different ways we can fill in a row. So do you notice anything if we write these numbers in binary? Well, when we write any of these triples in binary, you'll notice that in each triple, there's a total of 3 ones when we write it in binary. One of these ones lies in the ones place. One of them lies in the twos place, and one of them lies in the fours place. So for example, if we take 0, 1, 6, there's 1, 1 in the ones place, which comes from 1. There's a 1 in the twos place, which comes from 6. And there's a 1 in the fours place, which comes from 6 as well. And similarly for the other triples. So basically, given the structure, we can consider the binary representation of each of the numbers in the grid. Now, in each row, there has to be 1, 1 in the ones place, and same with each column. So we have to pick 3 appropriate squares to put a 1 in the ones place. Since each row has to have a 1 in the ones place, and each column has to have 1, 1 in the ones place, that means that there are 6 ways to assign the ones place. And by the same token, there are 6 ways to assign the twos place and 6 ways to assign the fours place. And since these choices are independent, you can check that any assignment is going to satisfy the problem condition. Then you can just multiply these independent cases. And that's why our answer ends up being a perfect cube, which might not be obvious if we slog through the casework. So this isn't really part of our casework topic, but this is a nice approach for otherwise bashy problem. So going back to casework, Dithya will be talking us through the next example.
All right, so our next example is this Amy problem, so I'll give you a couple of minutes to think about it. Okay, so to start this problem, we have a pretty weird condition here. So one thing we might try to like analyze this function is to look at the differences between consecutive values. So if we let y equal to x plus 1, then we have that f of x plus 1 minus, the absolute value of f of x plus 1 minus f of x is between 1 and 3. So we can let this difference be g of x. And now from the given condition that f of 0 is 0 and f of 6 is 12, we can write that g of 0 plus g of 1 plus g of 2 plus g of 3 plus g of 4 plus g of 5, which telescopes to f of 6 minus f of 0 is equal to 12. And also we have this, in addition to this sum, we already have this condition that the absolute value of g of x is bounded between 1 and 3. So now this sum is quite large considering that the maximum value of g of x is 3. So one question we might ask is how many times can g of x be negative when x goes from 0 to 5? Okay, so if we remember that the maximum value of g is 3, then like the claim is that that only one of these values at most one of these values can be negative, and so we can easily prove this. If there are two values that are negative, then the maximum value of the sum of g of 0 of g of 0 plus g of 1 plus g of 2 plus g of 3 plus g of 4 plus g of 5 is has to be at most 3 times 4 plus 2 times -1, because the smallest negative value here is -1 and the largest positive value here is 3. So this is equal to 10, which is less than that sum should have been. So this means that it can't decrease twice. So it can only be negative exactly once, or it can be negative at most once. So this motivates us to look at casework on how many times it's negative. So the first case is if it's never negative. So when it's always positive, this case is pretty simple to handle because we are choosing values for g of x between 1 and 3. And we know that the sum of all of the values is 12. So if we let g of x be equal to 1 a times, it's equal to 2 b times, and it's equal to 3 c times, then the total sum of g of x from 0 to 5 is a plus 2b plus 3c, and we know that's equal to 12. But also, there are 6 values of x here, so a plus b plus c is equal to 6. So from this, we can find all of the integer values for a, b, non-negative integer values for a, b, and c. So we can subtract both of the equations, so b plus 2c is 6. And if we look at this equation, there's 4 pairs for b and c, and we can substitute back into one of the first two equations to find the value of a. So we get these 4 pairs for how many times g of x is equal to 1, 2, and 3. But note that the function f is determined by the function g, but we still haven't technically determined the function g because we've just found how many times each value occurs, so we still need to order the values. So the number of ways to order is the following, because right, because some of the values are repeated, so we have to use these multinomial coefficients. So if we do this, the sum is 1 plus 30 plus 90 plus 20, which is 141. So this finishes the case when g of x is always positive. So now we can move on to the case when it's negative exactly once. So now in this case, it's a little bit more tricky, but if we were to substitute y is equal to x plus 2 in our initial inequality, this would give that f of x plus 2, the absolute value of f of x plus 2 minus f of x is between 2 and 6, which implies that the absolute value of g of x plus g of x plus 1 is between 2 and 6. So now, if we think about if we think about what happens when one of these values is negative, like say g of x is negative, well, um, if g of x is negative, then g of x plus 1 is positive, but because we only have one negative value. But we also know that the absolute value of their sum is between 2 and 6. So if g of x is negative, then we have to have that um, it's it's equal to -1, and g of x plus 1 is equal to 3. Otherwise, this absolute value won't be bounded. It won't be in this range. Because if we had like g of x is -2, then um, g of x plus 1 can be between 1 and 3, and the sum in that case would be between, it could be between -1 and 1. So it wouldn't be between 2 and 6. So we have to have, so we can check the cases, and we see that if one of these is equal to -1, then the other has to be equal to 3. So this means that wherever we have a negative value, it has to be equal to -1, and all of the consecutive values have to be equal to 3 if we just applied this result. So first, let's see what happens when the -1 is at one of the ends. So if g of 0 is -1, then this means g of 1 is 3. And now we have 4 values of g left that are not determined yet. But remember that the sum of all of these values of g has to be equal to 12. So if we use that, then g of 2 plus g of 3 plus g of 4 plus g of 5 is 10. And we can sort of just do the same thing as we did in the previous case. If there's like a times where a1's here, b2's, and c3's, then a plus 2b plus 3c is 10, and a plus b plus c is 4. And we can find that the triples here are 1, 0, 3, and 0, 2, 2. And the number of ways to order each one is 4 and 6, respectively. So the sum here is 10. And we get the same, it's completely symmetric if g of 5 is -1. So we have another 10 possibilities there. And the next case is if the -1 is not at the ends. So if it's somewhere in the middle, say for example, g of 1 is -1, then the two consecutive values, g of 0 and g of 2, have to be equal to 3, as we saw before. And now if we use the sum of all of these values of g is 12 again, then we get g of 3 plus g of 4 plus g of 5 is 7. So then we can use the same procedure as before to find that across these three values, we either have 1, 1, and mm, the first pair should say 1, 0, 2. Okay, the first pair should say 1, 0, 2, and the second pair should say 0, 2, 1, I believe. But the result is the same. We get that there are 6 cases in total. So so we have 6 functions here when g of 1 is -1. And we have 6 more in each of these cases when g of 2, 3, and 4 is -1. So this means that our answer in the final answer is 141 plus 2 times 10 plus 4 times 6, which is 185. So does anyone have any questions? Okay, great. So I think um, I think Brian will be taking over, and our next section is on symmetry.
Actually, I'll begin symmetry. So yeah, as Aditya said, that was our last casework question. Now we're going to talk about symmetry. So some counting questions have a certain notion of symmetry, and the following is a pretty easy example. So how many ways are there to arrange n people around the table if rotations are indistinguishable? And of course, the people are all distinguishable. So of course, the answer to this question is just n minus 1 factorial, because there's n factorial ways to arrange them around the table, and then each arrangement has n rotations. So we can split all the rotation, we can split all the n factorial arrangements into groups of n, which represent equivalence classes under rotation. And an easy way to tell if a question involves symmetry is it will include words such as indistinguishable, or involve something that can be spun or flipped, like a cube or a circle. And often the most important part of these questions is to find out how exactly the symmetry works inside the construct. And as stated, the reason why we can just divide by n in the above example is because that all groups of equivalences under rotation have size n. Unfortunately, this isn't true in general, and we'll see an example of this shortly. And so when beginning symmetry questions, it's very important to find these equivalence groups. So here's an easy example. I'll give you a moment to read it. And if you have any ideas, feel free to type them in the chat. Yep, so as people have noted in the chat, we can use Burnside's lemma. Unfortunately, we don't know what that is. So we're going to try to solve this without Burnside's lemma. So I guess we can get started. So first of all, as we'll replace the 3 colors with n colors. And we'll first solve the question with the without the restriction that we need each color at least once. So note that there are 6 possible symmetries. If we draw the Venn diagram symmetrically, we have 3 possible flips and 3 rotations, either a 120-degree clockwise or 120-degree counterclockwise. So as people have said, there are 6 total values of symmetry. And since there's 8 regions, each one with n ways to color, it seems like our answer would be n to the 8th over 6, just like what we did in the previous question with n factorial over n. But why is this wrong? So the reason why is that in the previous example, in our equivalence classes under rotation, every single class had the same size, or was the same size. But it's not true in this case. For example, an easy case is if everything is colored the same color. Now there's only 1 symmetry, not 6, because no matter how we rotate, we always end up in the same situation. And this didn't arise in the previous question because we assumed that everyone was distinct. So in this case, we can't just blindly divide by 6. So what do we do? Note that 6 is the maximum possible number of elements in these quote unquote symmetry classes. So all symmetry classes have a divisor of this number of elements. So either 1, 2, 3, or 6. So let's go through them one by one. First, let's call the regions R empty set, RA, RB, etc., denoting the regions. So RA is going to denote the region only, which is in A but not B or C. RB is going to denote in B but not A or C, and so forth. And note that R naught and RABC are always invariant under rotation, so they don't really matter. So we're going to go ahead and ignore them for now. So how many symmetry classes have size 1? So this means that no matter how we permute A, B, and C, they're always invariant. So what this means is that we can permute A, B, and C arbitrarily, and all the regions are still going to be colored the same. So this means that RA and RB and RC all must be colored the same color since they can be swapped at will. And likewise, RAB, RAC, and RBC are also all the same color, so they can be swapped at will. But the 2 common colors of these 2 groups are independent. So this tells us that there are n squared colorings with symmetric class size 1. And technically there's n to the 4th, but remember we're ignoring our empty set and RABC. So how about symmetry classes with size 2? Well, this is actually a trick question. None of them do. And the reason why we can see this is that we look at just the 3 colors in the middle. So if they're all the same color, then we're going to have, let's say, 1 way to rotate them. But if there's even 1 different, now there's 3 ways to rotate them. So it's going to be we either have that the number of elements in a symmetric class is 1, or it's going to be divisible by 3. So 2 is not a case. On the other hand, we can have some symmetry classes of size 3. And this means that both S1, which is the set of regions with which are part of exactly one of A, B, and C, and S2, which is a set of regions which are part of exactly 2 of A, B, and C, each have at most 2 distinct elements. Because if, say, RA, RB, RC are all different colors, then of course permuting A, B, and C is going to change the color, is always going to change the coloring. So it's actually part of a symmetry class of size 6. So each of these has at most 2 distinct elements, but at least one of them has 2 distinct elements. Because if they both have one distinct element, then we're back into symmetry class sizes of symmetry class size of 1. So this means that we either have 1, 2, 2, 1. The last case is supposed to say 2, 2, not 1, 1. So our 3 cases are 1, 2, 2, 1, and 2, 2. So for 1, 2, we can choose an arbitrary color for S1. There's n ways to do that. And we choose 2 colors for S2. So n ways to choose the one which appears twice. N minus 1 ways to choose the one which appears once. And then now note that there's 3 ways to orient it. The unique color can be A intersection B, A intersection C, or B intersection C. So we get 3n squared times n minus 1. And we also get this for 2, 1, since it's symmetric. And for 2, 2, we're going to choose 2 colors for each of S1 and S2. So each one has n times n minus 1 ways to choose. But note that we can't choose their orientations independently, because the unique color must be in the same sector. Since if they're in different sectors, then we can see that we're actually in a symmetry group of size 6. So we only multiply by 3 once. So this class gives 3n squared times n minus 1 squared. So in total, we add 3n squared times n minus 1 times 2, and then plus 3n squared times n minus 1 squared. So in total, we have 3n squared times n squared minus 1. And finally, how many have symmetry class of size 6? Well, if it doesn't have 1, 2, or 3, then it has to have symmetry class size 6. So all the remaining ones. So we just subtract everything we have so far from n to the 6th. And this gives n to the 6th minus 3n to the 4th plus 2n squared. So our answer is going to be n squared times the quantity, the number in symmetry classes of size 6 over 6, plus the number in symmetry classes of size 3 over 3, and then plus n squared. And then we multiplied by the n squared because remember we disregarded the R empty set and R ABC at the beginning. And adding these together and multiplying by n squared gives n to the 8th plus 3n to the 6th plus 2n to the 4th all over 6. So this tells us that if we have n colors, the number of ways we can color everything is going to be f of n is equal to n to the 8th plus 3n to the 6th plus 2n to the 4th over 6. Well, how do we finish? Remember that we disregarded the condition that they all had to be that there had to be at least one of each color. So when we compute f of 3, some of the cases we have only have 2 colors. So we just subtract them out. The number of ways to have the colors A and B, to only have colors 1 and 2, for example, is f of 2. So we do f of 3 minus 3f of 2. But when we do this, we subtract the case where there's only one color too many times. So we need to add it back in. So we add an extra f of 1. Not f of 1, we add an extra 3. So this is because f of 3 includes every single one of the cases exactly once. Every single one of the cases where there's only one color exactly once, and then we subtract it, and then we need to add it back. So our answer is 1248. Are there any questions on this question? Yeah, so there's a typo, it should say 3F1. Okay, so now we're gonna talk about, now Brian is gonna talk about Burnside's lemma. And we'll see easy ways to solve questions like these without getting into symmetric class arguments.
Right. So like as we saw with like the last problem, it can get pretty ugly if we try to do a lot of like computations like this. Right. So now we're going to introduce a new lemma called Burnside's lemma, which is like kind of a lemma we can use to solve like all of these kinds of problems. Right. So now, so the statement of this is basically, it looks complicated, but we're gonna do an example to kind of go over what it means. But basically, like it requires like looking at how many fixed sets like each symmetry has. And like the proof is non-trivial, so we're not gonna go over it. But so the notation's kind of like confusing, which is why we're just gonna do an example with it. So yeah, here's our example. So basically, the statement of Burnside says that if we take the average of the number of fixed configurations, where like in this case, a configuration can be thought of as like the, like for example, the colorings of the cube in this case. If we think about these, if we think about the fixed, like these fixed configurations, then for each symmetry, then we can basically just, if we take the average of this over all the symmetries, then we claim that this is going to equal the number of configurations up to those symmetries that we described. So now, in order to do this, we have to state what the symmetries are. So then, like, we'll try characterizing them. So we see that there are 24 total orientations of a cube. Basically, like we can choose any face to be the top face, and then we can choose any of the other 4 faces that are not opposite to it to be the face on the front. And then so we see that each of these corresponds with a unique orientation of the cube. And then so that's 24 total symmetries. So now we want to think about like, what do these symmetries look like? So, well, we'll just start listing them. Right, so like, how would we characterize these? Well then, like instead of just a top face with a front face. Like we want to find a more descriptive way of describing them, right? So, well, we can just not do anything. And there's one way for us to not do anything. And this is our first symmetry. And then we can also rotate 90 degrees around the face. And so there's 6 ways to do that. Because there's like 3 axes of faces, and each one can be rotated clockwise or counterclockwise. So that's 6 possibilities for that case. And then our next case is we can rotate 180 degrees around the face. And then here, like we have the same 3 axes as before, but then we're just gonna rotate 180 degrees. And then, so that's just 3 possibilities there. And now we can rotate 120 degrees around a space diagonal. There's 4 space diagonals, and each of them, we have 2 possible rotations, like clockwise 120 degrees and counterclockwise 120 degrees. So this gives us 8 more symmetries, and then the last 6 symmetries come from 180 degree rotation around the face diagonal. So like essentially, if you like took 2 opposite edges and then flipped both of them upside down, then that would be the symmetry, right? And then we can see that these cases all add up to 24 total cases, and so that confirms like that we do have all our symmetries. Right, so now we're going to use Burnside's lemma based on these symmetries. Right, so basically what we want to count with Burnside's lemma is we want to count the number of colorings that are fixed by this symmetry. So for example, our first case will be the identity. So the identity, every coloring of the cube will be fixed. Like it will still be the same coloring. So that means that like we just choose any of the n to the 6th and they will all work. So there's n to the 6th possibilities here. Now under a 90 degree face rotation, well, we have the 2 faces on the ends that will not move, but then the other 4 faces like around the middle will cycle into each other. So they all have to be the same color, and then the 2 faces on each end can both be whatever they want. So that's 3 choices that we can make. So then that gives us n to the 3rd possibilities. So now our next case is a 180 degree face rotation. Right, so again, here our 2 faces at the ends will not move, they're fixed. But then instead of having a big 4 cycle around the middle, we have the 2 opposite faces will swap. So now that means that like they can be, like the 2 opposite faces still have to be the same color, but then they can be different colors from each other. So now we have 4 choices here. So what this means is there are n to the 4 possibilities in this case. So now we can go to our next case, which is the 120 degree space diagonal. And then, so here what we can see happen is, so the space diagonal has 2 endpoints. So the 3 faces around each endpoint will all go to each other. They will each form 3 cycles, and then same thing at the other endpoint. And then so we have two separate 3 cycles. So that's 2 choices. So that's n squared possibilities. And then if we have the 180-degree phase diagonal, well then we can have like 2 opposite faces will swap, and then the other 4 faces will come into pairs that will swap with each other, like so that the 2 next to each other will swap. And then so this gives us 3 total, 3 choices. So then this tells us that it's n to the third in this case as well. Right, so now we use Burnside's lemma, and what Burnside's lemma says is that if we just average this, like for example, 3n to the 4 comes from the fact that there are 3 180-degree phase rotations, and then each of them has n to the 4 cases that are fixed. If we just add this up, then this gives us our total sum, right? And then so that's our answer. And you can see how a method like this can be used to solve like the previous question, for example, where you just list out all the possible symmetries and then count how many colorings are fixed. Right. So for the previous question, we had like a Venn diagram, right? So basically our symmetries can come in, so our possible symmetries are we don't do anything, we rotate it by 120 or 240 degrees, or we choose one of 3 axes to flip across, right? So, and then basically, in the identity case, there's n to the 8 possibilities, and then in the reflection case, there's n to the 6 and n to the 6 possibilities, because like everything is fixed except for there's one pair there's 2 pairs that swap, so that's 6 choices there. And then in the last case of a 120-degree rotation, there's the empty set and the everything set will both stay fixed, and then the sets with 1 element and the set with 2 element form 2 cycles. So that's n to the 4 possibilities there. And then so we get like n to the 8 plus 3 n to the 6 plus 2 n to the 4 all over 6, which is what we had from before. Right. So yeah, are there any other questions? If not, I think we're done for today.
Yep. So this was our last question. So if there are no questions, that's it. Thanks everyone for coming. And we hope to see you next week for our continuation on counting.